Here is a monochromatic X-ray source. This tool can emit light with the same wavelength, or one wavelength value. Thin sheet metal. Usually it is graphite. In this metal there are free electrons. And a detector to detect electromagnetic waves. The arrangement of this device is an illustration of the Compton experiment. How does this system work? In this case, we will review this system in a different perspective: predictions from classical physics and experimental data. First is the prediction of classical physics. The X-ray radiates to the right. This beam hits the electron. Next, the X-rays deviate from their original direction. So are electrons. To detect the scattered light, we can put a detector here. On the detector screen there is one wavelength with maximum intensity. That is, the value read is the wavelength. Similar to the process of light reflection, the wavelength of the reflected light is the same as the wavelength of the incident light. Because the light is scattered in all directions, then we can put the detector at any deviation angle. The value read by the detector for each deviation angle is one value, which is none other than the wavelength of the incident light. So the shape of the intensity curve is the same. This is the prediction from this experiment based on classical physics. The second is experimental data. The X-ray radiates to the right. This beam hits the electron. Next, the X-rays deviate from their original direction. So are electrons. To detect scattered X-rays, we can put detectors here. Apparently, the detected wavelength is not one value, but there are two values. Because on the intensity curve, there are two wavelengths that have maximum intensity values. What does it mean? It means that at this point there are actually two wavelengths. The first wavelength is similar to the wavelength of flat light. The second wavelength is the scattered wavelength that is not yet understood. The shape of this curve is unique for each particular deviation angle. That is, the value of the unintelligible scattered wavelength is different for each deviation angle. In general, the value of the scattered wavelength is always greater than the wavelength of the incident light, or all of the light. When compared between the theory of light waves and experimental results, it turns out they don't match. In other words, the wave theory cannot explain the experimental results of the scattering of X-rays. We will study this in the next series.